Hello students, in this video we'll understand the connection between conformal minimal surfaces and analytic functions or holomorphic functions. Let's consider a conformal, we've also called these isothermal, minimal surface. Okay. R of U and V, like this, with first fundamental form e to the 2 f du squared plus dv squared. In this case, we know that we can actually write down an equation for the Laplacian of this then recall that the Laplacian of r is equal to twice the scalar curvature times this conformal factor over here, right? So we know that this is going to be a minimal surface if and only if we know that for these minimal surfaces, since it's minimal, I know scalar curvature is equal to 0, and therefore the Laplacian of r is equal to 0, right? So that's one thing we've already proven. Okay. And so now what we want to do is we want to show, let's consider now, let zeta be u plus iv, where here I is the principal square root of -1, right? The complex number -1. Now, of course, what I have here is I have a function r of u and v. I can think of r as a function of a complex variable. Then define psi of zeta, and what will psi of zeta be? It's going to be r sub u, okay, and it's going to be a vector holomorphic function, r sub u minus r sub v, like this, right? And then, of course, what we're going to say is we're going to say that we claim then psi is analytic or holomorphic They mean the same thing, analytic functions, holomorphic functions. If and only if this surface over here, if and only if R is a conformal minimal surface. Okay. And recall, what does it mean to be holomorphic, right? So recall that a function g mapping the complex plane into the complex plane is holomorphic on an open set omega if and only if it satisfies the Cauchy-Riemann equations, right? If and only if it satisfies Cauchy-Riemann. And of course the Cauchy-Riemann equations, which we've proven in a previous video, okay? And so, of course, what there are the Cauchy-Riemann equations, they say that partial g, partial x is negative, partial is, let's do it like this actually. So we're going to have to write this in terms of real and imaginary parts. So let's write g. If g is a plus ib, and these are functions of x and y, so that's really a of x, y plus ib of x, y. Then this means what? This means that partial g, partial a, partial x is partial b, partial y, and partial a, partial y is negative partial b, partial x. Those are the Cauchy-Riemann equations for the real and imaginary parts of the function over here, right? And so what do we need over here? So let's look at the vector Cauchy-Riemann equation. So for us, what can we say? So now we need what? So psi of zeta is analytic, therefore, or holomorphic. You can notice that I'm saying analytic and holomorphic interchangeably, right? Depends on where you basically learn your complex variables, right? So the different schools of thought, you can read Rudin's book. Rudin calls them holomorphic functions. Other books call them analytic functions. Analytic is usually a term that's more reserved for like a real variable function, right? We say real variable functions are analytic, and typically complex valued functions are holomorphic, right? So I'm going to interchangeably use these terms, right? So don't get confused by them, right? So psi is analytic if and only if, well, what's the real part? So this is my real part of psi, so I need that ru, that's my u component, my x component, is equal to what? Well, this Cauchy-Riemann equation over here has to be equal to what? It has to be equal to negative RV, that's the imaginary component, with respect to the second component V. And that's the first Cauchy-Riemann equation. The second Cauchy-Riemann equation is going to be RU with respect to V. It has to be negative of negative RV with respect to U, right? Now this equation over here, this expression is always satisfied, right? That's always true for a continuously differentiable function. Second continuously differentiable, always true because mixed partials are equal, right? Because I know that RUV is equal to RVU, because if it's sufficiently regular, that's going to be true, right? Now the second condition over here, this condition over here is valid. This, of course, that condition is really saying RUU minus RVV is equal to 0, right? Is equal, not equal to 0, but just equal to RVV. And so this implies what? This implies that we need that RUU plus RVV is equal to 0, right? But that's true if and only if the Laplacian of R is equal to 0, which we know is true, right? Because of this formula here, which we proved in a previous video, right? So in other words, we know that this function psi of RU minus RV is going to be an analytic function. Now the other remarkable thing to check about this is that this function psi has some particular properties, right? So if we write out psi in terms of its components, right? So proposition, we claim that for this minimal surface, so for our parameterization of a conformal minimal surface, we have psi 1 squared plus psi 2 squared plus psi 3 squared is equal to 0, okay? Of course, this psi, of course, has three components, an x, a y, and a z component, because we're making the surface from R2 into R3, right? And so how do we see this over here? So if we write R as x, y, and then z, right? Then what will this be? So here's the proof of this fact. So the proof is straightforward, right? So psi 1 squared is going to be x. Now, what's that going to be? So I really have a y. I really have an xu minus rxv, right? That's going to be an xu minus ixv squared. And then plus, let's do all of them together, actually. So to save myself a little bit of space, let's do them all together. So psi 1 squared plus psi 2 squared plus psi 3 squared is going to be xu minus ixv squared plus yu minus iyv squared plus zu minus izv squared, like so. And so we're going to the pure squared terms. What are the pure squared terms over here? The pure squared terms are going to be xu squared plus yu squared plus zu squared. What's that going to be? Well, that's just going to be ru, the length of ru. So it's going to be the length of ru squared. Then we're going to have a negative I squared xv squared, negative I squared yv squared, negative I squared zv squared. That's going to be what? That's going to be equal to well, I have the I squared is going to be negative 1, so it's going to be a negative, and then that's going to be RV squared. And then what are the mixed terms going to be? The mixed terms are all going to have a negative 2i, and then it's going to be an xu, xv, yu, yv, zu, zv. That's just going to be ru dot rv, right? Now I know that ru dot rv is equal to 0 because it's a conformal metric, so that term over there is equal to 0. And since it's conformal, this is really my e over here, and this is really my g, but e and g are equal to each other, so this whole expression is equal to 0, right? This whole expression is equal to 0, and this vector field psi, for it to be a regular surface, can't be equal to 0. So for a parameterized conformal surface, we have that this condition is true, and we have that psi itself is not 0. Because if psi was 0 by the analyticity, that would force this term to be 0 and this term to be 0, and we wouldn't have a regular surface. So we've just shown that for a for a conformal minimal surface, we have this condition, psi 1 squared plus psi 2 squared plus psi 3 squared is equal to 0, and psi is not 0 for this analytic function over here, RU minus IRV. In the next video, we're going to see that this condition over here, if I have this condition that the sum of the squares of the components of psi are equal to 0 and that psi is not identically equal to 0, I can use this condition over here to actually construct a surface, and that surface is going to be a conformal minimal surface. And we'll see examples of how we can use that formulation to generate minimal surfaces from analytic functions. Thank you very much.